Nucleus. Are you able to hear me?
Yes, sir.
Yes, sir.
Get started. So the next chapter, that is nuclear. So you're able to see the screen, right? So this is chapter number 13. So yesterday we saw the 12th chapter that was based on atoms. So we understood that atoms consist of what? Atoms consist of electrons, protons, and neutrons. So these protons and neutrons collectively is formed in a central core called as nucleus. And this chapter is about the nucleus. The previous chapter was all about an atom and its structure, and the stability of an atom was explained. Whereas in this chapter, we'll be more concerned about how a nucleus or what particles does a nucleus consist of, and its properties. Okay. So the topics covered in this chapter are: first, we will see the introduction to nuclei. Then we will see the next concept of atomic masses and composition of nucleus. Then we'll go to the next concept of the size of the nucleus. Then we will see the mass, energy, and nuclear binding energy. Then nuclear force. Radioactivity is not there. In nuclear energy, we will talk about the fission and the fusion reactions. Okay. This is also a very small chapter, as I mentioned previously. Max will be completed by tomorrow. But small. So we'll get started with the concept of nuclear. So we know the fact that there were different models of atoms that were proposed. Right. In one of it, the J.J. Thomson's model. So after J.J. Thomson's model, what happened? There was a scientist named Rutherford who did an experiment to check the structure of atom. So during that process, the atomic nucleus was discovered, right? So that was the first time that we understood that there is something called as a nucleus, which consists of all the positive charge concentrated at that place. So the atomic nucleus was discovered by Ernst Rutherford in the year 1911. So his experiment of alpha particles, scattering of alpha particles, proved that the whole mass of the atom and the positive charge is concentrated in a very small central core called as the nucleus. So at that point, when he coined the term nucleus, people thought that nucleus consisted of only positive charge. That is, it consisted of only positively charged particles. But in today's world, we know the fact that nucleus consists of positive charges plus what else does it consist of? The positive charges are called as the protons. Along with protons, what does a nucleus consist of?
Neutrons.
Neutrons.
Of neutrons. But at the time when Rutherford discovered nucleus, they didn't know about the concept of neutrons. Okay. So that's what they told. Positive charge is concentrated in a very small central core called as nucleus. And according to them, the positive charge was only protons. So the dimension of nucleus, obviously, okay, the dimension of nucleus is much smaller than the overall size of the atom, and the nucleus is surrounded by orbiting electrons. All these things we know. Right. Now we need to know what basically a nucleus consists of. A nucleus consists of the elementary particles, that is protons and neutrons, and these two are collectively called as nucleons. So the collection of protons and neutrons is called as nucleons. Generally, a proton has a positive charge which is of the same magnitude as that of the electron, whereas if you talk about the rest mass of a proton, it is 1836 times greater than the mass of the electron. Okay. Similarly, if you take a neutron is electrically neutral whose mass is equal to almost that of the proton. Okay. Next is the nucleons inside the nucleus are held together by strong attractive forces called as the nuclear forces. Next is generally, if you take the nucleus of an element represented by the symbol XAZ, where X is the chemical symbol of the element and Z represents the atomic number, which is equal to the number of protons. So Z is the atomic number, which represents the number of protons, and A is the mass number, which is equal to the number of protons plus the number of neutrons. Okay. If you represent the number of neutrons as capital N, then that capital N will be equal to A minus Z, where A is the mass number minus Z is the atomic number. So, for example, if you take the chlorine nucleus, whose symbolic representation is Cl3517, then it contains 17 protons, 35 nucleons, and 35 minus 17, that is 18 neutrons. So this is the basic introduction of what does a nucleus consist of. Is it clear, guys?
Yes, sir.
Next. So once this is over, the classification of nuclei is what we are going to see. So nuclei are basically classified into different types depending on the number of protons they have, depending on the atomic number, depending on the mass number, and depending on the number of neutrons that are present. So first one is isotopes. Iso is same, right? Isotopes are those atoms of whom? Of the same element, which have the same atomic number Z but different mass number A. Okay, and the nuclei H11, H21, and H31 are generally the isotopes of hydrogen. Okay, in other words, what you can say is isotopes belong to the same element. They contain the same number of protons but different number of neutrons. So those elements which contain the same number of protons but different number of neutrons are what are called as isotopes. Similarly, as the atoms of isotopes have identical electronic structure, they have identical chemical properties and placed in the same location in the periodic table. Okay, so these are all the important points that are related to isotopes. Similarly, when you talk about isobars, isobars are those atoms of different elements having the same mass number but different atomic numbers. Okay, if you take the nuclei, oxygen 16 and nitrogen 16, they represent two isobars. So since isobars are atoms of different elements, they have different physical and chemical properties. So what is going to happen here is, in the case of isotopes, since they belong to the same element, they will have identical chemical properties, hence they are placed in the same location of the periodic table. Whereas in the case of isobars, isobars are possible only for different elements. Okay, so they will have different physical and chemical structure. The next is isotones. So isotones are atoms of different elements having the same number of neutrons. If you take carbon 14 has 8 neutrons, and oxygen 16 also has 8 neutrons. So these are the examples of isotones. Is it clear?
Yes, sir.
Right. The next is general properties of nucleus. So in general properties, we have 6 different properties that we need to understand, out of which the first one is called as the nuclear size. Means the nucleus is the central part which consists of finite size associated with it. So from the Rutherford's alpha ray scattering experiment and the distance of closest approach to the nucleus, If you take these two parameters to measure the radius of the nucleus, then the radius of the nucleus was approximately measured to be of size 10 power minus 15 meter, right? This is from the basis of Rutherford's experiment. Similarly, if the nucleus is assumed to be spherical, then you can always form an empirical relation. Empirical is something which is written based on observation. You will not have a statistical data, like you will not have a derivation for it. It is an empirical relation which is found to hold good between the radius of the nucleus R and the mass number A. So it is given by the formula R is directly proportional to A power 1 by 3, or R is equal to R naught into A power 1 by 3, where R naught is called as the R naught is the constant of proportionality and is equal to 1.3 F. F stands for Fermi. Generally, 1 Fermi is 1 femtometer, which is 10 power minus 15 meter. Okay, this is all about the nuclear size. R is equal to R naught into A power 1 by 3 is what you need to remember. Is it clear, guys? Second is the property that we'll be concentrating upon is nuclear density, which is represented by the symbol rho. So the nuclear density, or I can write it as rho n, okay, can be calculated from the mass and size of the nucleus. Okay, you can calculate it from the mass and size of the nucleus. So nuclear density, generally, how is density defined? Density is equal to mass divided by volume. So who constitutes to the mass of the nucleus? So nuclear mass is mass number times mass of each neutron, where A is the mass number. If Mn is taken as the mass of one nucleon and is approximately equal to 1.67 into 10 power minus 27 kilogram, then the density of nucleus is written as nuclear mass, that is A times mass of each neutron, sorry, each nucleon, because we know that the mass of neutron and the mass of proton are approximately the same and equal to 1.67 into 10 power minus 27 kilogram. So rho n is this value, and nuclear volume is equal to 4 by 3 pi r cube, right? Then the nuclear density will be equal to A times Mn divided by 4 by 3 times pi r cube, that is A into Mn divided by 4 by 3 into pi into R is R naught into A power 1 by 3 the whole cube, right? So this will give us 3 by 4 pi times A into Mn divided by R naught cube into A. A and A will get cancelled. This will give us 3 times Mn divided by 4 pi into R naught cube. If you observe, 3 and Mn are constant, 4 pi is a constant, and R naught cube is also constant. So taking all these values into consideration, we can say that the nuclear density is a constant. Okay, nuclear density is constant, and its calculated value is 1.816 into 10 power 17 kilogram per meter cube. Okay, so this value is approximately constant for all the nuclei that are present in this world, irrespective of their mass number, right? And you're able to see that 1.816 into 10 power 17 kilogram per meter cube is a very, very big number. And this high value of the nuclear density shows that the nuclear matter is in an extremely compressed state. Okay. I guess
Yes, sir.
Divyesh 1.2 or 1.3 will not make much difference, because it is already 10 power minus 15 meter. Okay, it is that small. Next is nuclear charge. Then, if you talk about the charge of the nucleus, it is due to whom? So nucleus consists of positive charge, but we know that nucleus consists of protons or neutrons. But who is constituting to the charge of the nucleus? It is the protons which are present in it. So each proton has a positive charge whose value is equal to 1.6 into 10 power minus 19 coulomb. And the nuclear charge is given by the value Ze, where Z is the atomic number of that particular atom. Is it clear? So this is a simple concept. Fourth one is atomic mass unit. So generally, if you take the mass of the nucleus, we will not represent the mass in terms of kilogram because it is very, very small quantity. It is approximately 10 power minus 27 times 1.617, which is like almost 27 zeros before that 1.7. So what we will do is we will introduce another unit which is convenient to represent the mass of the nucleus. So it is convenient to express the mass of a nucleus in a unit called as atomic mass unit, though the unit of mass is kilogram. So one atomic mass unit is considered as 1/12 of the mass of the carbon atom, and carbon of atomic number 6 and mass number 12 has a mass of equal mass of value 12 AMU, has mass equal to 12 AMU. And remember, 1 AMU is taken to be 1.66 into 10 power minus 27 kilograms. So what is atomic mass unit? It is mass of 1/12 of a C12 atom. Okay. So having this in mind, what we can say is the mass of proton is 1.007276 AMU. This is equal to the difference in the mass of hydrogen atom, which is 1.007825, and the mass of electron. Okay. Similarly, if you take the mass of neutron, it comes out to be 1.008665 AMU. So the moral of the story here is, instead of writing in AMU, if you write the mass of proton and mass of neutron in terms of kilogram, then you get the value as 1.617 into 10 power minus 27 kilogram only. Whereas when you write it in terms of AMU, this is the value that you're going to get. Okay. Then what we can say is the energy equivalence of 1 AMU can be calculated in electron volt. So remember, the next thing that we are going to learn is about the energy mass equation, which is E is equal to mc square. So this equation tells us that energy and mass are interconvertible. In the sense, if there is a particle which has a mass m associated with it, then it will have an equivalent value of energy E associated with it, which can be convertible from one form to another. So what they are trying to say is the energy equivalence. So mass is 1 AMU. If I take the mass as 1 AMU, then you can calculate the equivalent value of energy associated with it in terms of electron volt by using the formula E is equal to mc square. Now, E is equal to 1 AMU. 1 AMU is 1.66 into 10 power minus 27 kilogram. What is the value of C in terms of speed of light? Power 8 meters per second. So if you square it, you will get 9 into 1.66. When you multiply everything, so 1.66 into 9 into 10 power minus 19. So this value will be in terms of joule, but we want this to be in terms of electron volt. We know that 1 electron volt is equal to 1.602 10 power minus 19 joules. So how did we get this? That is where we need to see. 1 electron volt is defined like this. It is the amount of energy of an electron when it is accelerated through a potential difference of 1 volt. So if you have a potential difference of 1 volt existing and you want to accelerate 1 electron through this potential difference, then the amount of work you do is called as 1 electron volt. Remember, 1 electron volt is this much value. 0.602 into 10 power minus 19 Joule. Okay. So if I need to convert the energy to Joule, then E will be equal to 1.602 into 10 power minus 19. Sorry. 1.66 into 9 into 10 power minus 19 divided by 1.602 into 10 power minus 19. This and this will go, and this value will come out to be approximately 931.5 mega electron volt. So this is what we need to remember. So if anybody asks, what is the equivalent energy present for a mass of 1 AMU, then you need to put the answer as 931 or 931.5 mega electron volt, or we can also call it as million electron volt, because million is 10 power 6. Is it clear till this step, guys? Is it clear till this point? So we started with 1 AMU and we finished with 1 AMU is equivalent to how much amount of energy? Is it clear?
Yes, sir.
This is the fourth property. Then the fifth property is going to be nuclear mass. So if I talk about the mass of a nucleus, what are all the particles that constitute the mass of the nucleus? They are protons and neutrons put together. As the nucleus consists of protons and neutrons, the mass of the nucleus is assumed to be the mass of its constituent particles. So the assumed nuclear mass is going to be how much? Mass of each proton multiplied with the number of protons that you have, that is atomic number, plus mass of each neutron multiplied by the number of neutrons that you have, which is represented by A minus Z. Is it clear? Right, there's a very, very simple concept. So theoretically, if I have to write down what is the mass of the nucleus, then it is very clear that I should write it as Z times mass of each proton plus A minus Z times mass of each neutron, where MP and Mn are the mass of proton and neutron respectively. Okay. But generally what happens, right, when you measure these values practically, however, from the measurement of mass by using mass spectrometers, it is observed that the mass of the stable nucleus M is generally less than the total mass of the nucleus. So this is what happens. So what happens? If you try to measure it using a device called as a mass spectrometer, if you take a stable nucleus, then its total mass is going to be actually less than that of this assumed nuclear mass. So if the real mass of the nucleus, by measuring it practically, is always less than the theoretical mass that we proposed in the name of assumed nuclear mass. Okay. And if you are able to calculate this value, Z times MP plus N times Mn. So here, if you observe, I'm writing small n for neutrons and capital N for nucleons. Okay. If I write M capital N, then I'm trying to talk about mass of this capital N represents nucleons. Whereas if I write M small n, the small n represents neutrons. So have a note of this point. Okay. Then Z times mass of protons plus N times mass of neutrons minus M. I'll write it again. Z times MP plus N times Mn minus the actual mass of nucleus is what is termed as delta M. What is it termed as? It is termed as delta M. And this delta M is what is called as the mass defect. So make a note of this. This mass defect is a very, very important term. Make a note of this. I'll tell you what is the significance of it.
Sir, I have a doubt.
Please.
Why is it called the assumed nuclear mass?
Because that is what you're writing theoretically, right? See, we know the fact that a nucleus consists of what? It consists of a proton, sorry, consists of protons and neutrons, right? See, suppose you go to a shop, okay, you go to a shop and buy, let's say you're buying 5 apples and 3 oranges. And if I ask you, what do you think is going to be the mass of this? Let's assume all the apples are of the same mass and all the oranges are of the same mass. Then what will you write? You write 5 times mass of each apple plus 3 times mass of each orange. Is that what you're going to write? This you're writing using the logic. Correct? Are you able to
Yes,
understand?
sir.
So here, this apple is what is something similar to proton, and orange is something which is similar to the neutrons that are present. Okay, 1 minute. M small m. There is a correction here. It is m small m. So this is what we theoretically write even before this is put on a weighing scale. Is that right? So because you use the logic. So can I call this is the mass that you assume that is going to exist? But suddenly what will happen is you take this and put it on a weighing scale. That weighing scale is what is this mass spectrometer. You put it on a weighing scale. To your surprise, what is it you're able to observe? The mass that you calculated is not exactly this value, but it is slightly lesser than this. Okay. So what did you do? Even before you put it on a scale, you assume that this is going to be the mass, right? That is the reason why we call it as assumed nuclear mass. So the only difference is apples and oranges you can touch and see, whereas neutrons and protons you cannot touch and see. That is why we are assuming.
Understood, sir.
Got it? Yeah.
I have a doubt.
Tell me.
So this minus m, that m, what does it stand for actually? Sir?
That m is the mass that is measured using the weighing scale.
So how will it be given in the question, sir?
That I will tell you. Don't worry about questions.
Okay, sir.
That I will. Don't worry. So this is actually the theoretical mass, and this is the practical mass. Are you able to understand? So what happens?
Yes.
We assume there is going to be the mass, but to our surprise, what will happen? There will be a slight difference between the mass that we assumed and the mass that is actually present in the material, and that difference is what is termed as mass defect. So there is a reason why this is occurring, because so try to understand the difference in the total mass of the nucleons. So what do you mean by total mass of the nucleons? The protons and neutrons put together, you will get the mass of the nucleons and the actual mass of the nucleus. Why am I calling it as actual mass? Because that is the weight which is shown by the weighing scale. That is the mass spectrometer. Okay, of the nucleus is known as the mass spectrometer. Okay. Now, the important question that you might have got in your head is, why is this happening? It is because one thing you observe the density of the nucleus. It was, how much was the density of the nucleus? It was 1.8 something into 10 power 17 kilogram per meter cube. Means, is the nucleus not in a compressed state? Right. So what does a nucleus consist of? It consists of protons and neutrons. Now tell me one thing, these protons and neutrons, initially let's say these charges were at infinity. Right? Where are they? They are at infinity. So will there be any interaction taking place between these two positive charges? There will be no interaction taking place, right? But whereas when these charges are brought into a small area called as the nucleus, then what will happen between them? What will happen? There will be a lot of electrostatic repulsion that is going to act. So when a lot of electrostatic repulsion is going to act, we need to do the work against the system to bring these charges into a small sized space called as the nucleus. So when you're doing this, the protons and neutrons are going to get combined inside that small space. When this happens, then there should be some energy that is released so that there is a stability attained by that particular nucleus. Or else what would have happened? The nucleus would have been unstable. If nucleus is unstable, what would have happened? There would be a nuclear reaction that is taking place. But it is not happening naturally for all the nucleus, right? Is it happening? Naturally, not all the nucleus are going to be unstable, except radioactive elements which are going to be unstable. We don't think of any other nucleus which is unstable. So when this is kind of happening, see, when the protons and neutrons combine to form a nucleus, the mass that disappears. So why we are saying mass that disappears is because we know that according to this relation E is equal to mc square, energy and mass are equivalent. This is called as energy mass equivalence reaction. Means energy and mass are equivalent and they can be converted from one form to another. They can be interchangeable is what the point says. When that is going to be the case, then this mass that is disappearing is converted into an equivalent amount of energy, which is called as delta mc square. And this energy, which is released during the process of the protons and neutrons getting combined together, is what is called as the binding energy of the nucleus. Okay, are you able to understand? So why is this mass defect coming? This mass defect is coming because of the formation of the nucleus itself. When protons and neutrons combine to form that nucleus, then there is some energy released in the form of, okay? And that energy that is released is what is called as binding energy. Hence, the equivalent amount of defect that is taking place in mass is what we call it as mass defect. And binding energy is given by the formula. So E is equal to mc square. Binding energy is equal to delta mc square. So binding energy is corresponding to the mass defect that has taken place. So binding energy will be, can I write it as Z times mp plus n times mn minus the mass of the nucleus into c square. Can I write it like this? Guys, yes or no? Is there any doubt? Is it clear?
Yes, sir.
Okay.
Clear,
Now
sir.
what happens is the binding energy of the nucleus determines its stability against the disintegration. So what they're trying to say is more is the value of binding energy, more is going to be the stability of the nucleus. Right? Stability of whom? Not the stability of atom. There is a difference. Okay. An atom is said to be unstable when the electrons are in excited state. Let's try to understand the difference. You'll be hearing about the stability for atoms and nucleus. So here, what is our concentration? Our concentration is about the nucleus itself. So atom as a whole is said to be unstable when the electrons are in excited state. Whereas a nucleus is said to be unstable when the binding energy of it is less. Okay. In other words, if the binding energy is large, the nucleus is stable and vice versa. That's what happens. Is that clear? So this is a very, very important point. Make a note. Then we have the concept called as the binding energy per nucleon. So what is happening? You know how to calculate the binding energy. That is, you will use the formula delta m c square. So they'll give you the mass and your job is to find the mass defect and multiply it with c square, correct? So binding energy per nucleon means you calculate the binding energy of the nucleus first and divide it with the total number of nucleons that are present. So total number of nucleons that are present is nothing but the mass number. Right. So it is found that the binding energy per nucleon will vary from element to element, and you can plot a graph which shows the binding energy per nucleon versus the mass number, and this is the graph that you will have. Okay. So actually, as per the syllabus, this binding energy curve is not there, but I have to explain this of how the numbers have come for you to understand the concept of fission and fusion. Only then you will have a conviction that why binding energy is important. Okay. So it is a very, very small step. Just you will understand it less than 5 minutes. Okay, just give me a minute. It is. Listen. This nuclear binding energy is there. No? See, if I take this example 13.3, find the energy equivalent of one atomic mass unit. So I already told you one atomic mass unit is equivalent to how much amount of energy in terms of electron volt. It is equivalent to 931.5 million electron volt. Accepted. This we have already calculated. How did we get this? We know that E is equal to mc square. So one atomic mass unit is 1.66 into 10 power minus 27 kilogram into C square is 9 into 10 power 16, right? These many joules will come. To convert joule to electron volt, you need to divide it with 1.6 into 10 power minus 19. When you do this, what are you going to get? So when you do this, what will you get? You will get the value as 931.5 million electron volt. Okay, but see, using this, express the mass defect of oxygen. What are we supposed to do? Express the mass defect of oxygen in million electron volt per C square. So how do you do that? So one atomic mass unit, can I write it as 931.5 mega electron volt divided by C square. How did I get that? Because one atomic mass unit. So atomic mass unit, I believe that everybody knows that it is represented using symbol U. You would have learned in your chemistry. Into C square will be equal to 931.5 million electron. Is that right? So 1 U is equal to 931.5 divided by C square. Right. Then how much is going to be the mass defect of oxygen? So the thing is, you need to know the mass defect of oxygen. One mistake they did is they didn't give you the value of each particle. So the mass defect of oxygen, this you can take it from the table. They should actually give it to you in the exam. Mass defect is 0.13691 U. But remember, 0.13691 into U can be written as 931.5 mega electron volt. Okay. So it will be 931.5 mega electron volt per C square. So if you multiply both, you will get the answer as 127.5 mega electron volt per C square. So what is happening here is, wherever you have the atomic mass unit, just replace the atomic mass unit with that 931.5 million electron volt. That's it. That is what you need to do. Okay. Is it clear, guys? So now the question is, how did we get this mass defect? That is what I want to show you. For that, I need a problem. I'll go to the exercise problems. See. Obtain 13.3. Obtain the binding energy in million electron volt of nitrogen nucleus given the mass of nitrogen is how much? Is 14.00307 U. Right? Did you understand this? Now listen. You need to find the binding energy in terms of million electron volt. Correct? So binding energy is equal to how much? Delta M C square. Accepted? But we know the fact that if you know the mass defect in terms of AMU, you replace that one AMU with 931.5 mega electron volt, that will give you the answer. So to calculate delta M, what is the formula? Z times mass of proton plus N times mass of neutron minus small m. Mass of neutron minus small m. So Z is how much? 7 into mass of proton is given here. Where is it? Mass of proton in this context, we can take it as the mass of hydrogen itself, which is 1.007825. This is what I told you they should give you. Plus N is how much, guys? N is also 7, because capital N is how much? 14 minus 7 into what is the mass of each neutron? 1.008665. Okay. Minus what is the mass of the nucleus that they have given? 14.00307. So for this problem, we can use calculator. Can you guys use calculator and tell me what is the answer for this thing? 7 into 1.007825. What is the answer? Please tell me. Hey, what are you people doing? Are you there or not? I asked a simple thing. What is? Tell me, what is it? Use calculator and what are you people? You're breaking your head for that. Use it to 7 into 1.007825. What is the answer? You want me to do that also? Rohan, make it faster. Please tell me.
Yes, sir, just a minute.
Yeah.
Sir, I got the final answer as 0.11236.
Okay. 236. Okay. Let's say this is the answer. Okay. So what is this actually that you have calculated?
Mass.
You have calculated mass defect, right? So mass defect is these many AMU. So logic is 1 AMU is equivalent to 931.5 million electron volt. Then 0.11 into 236U will be equivalent to how much amount of energy? What will you do? If I call this as
931.5.
yes. So you'll write 0.11236 into 931.5. What is the answer, guys? Can use calculator.
Hundred 4.66334.
4.66,
104.66.
okay, 104.66, 104.66
Same as
million. Sorry, I'm leaving it as it is. Okay, this is the binding energy. If I want the binding energy per nucleon. 104.66 divided by how much should be the value of A? This is what atom or what nucleus? Nitrogen nucleus. So nitrogen nucleus now it should be 14 here. So இது எவ்வளவு சொல்லுங்க? How much is this value?
7.47.
Yes, sir, 7.47.
Sorry, I had some network issue. Till when was I audible?
So the value is
So you also have to calculate 104.66 by 14.
104.66.
binding
So I
energy.
finished from. Yeah, correct. So my voice stopped there itself. Huh? I
Yes, sir.
spoke so much after that. So 104.66 divided by 14 gives you a value of 7.47 million electron volt. So this is the amount of binding energy per nucleon that is going to occur, correct? So if you look at this binding energy curve, then what happens is when you draw the value of binding energy per nucleon versus mass number, then we can understand. See, we took for the nitrogen atom, we calculated, no, now. So we calculated for nitrogen atoms. For the nitrogen atom, the binding energy per nucleon came out to be 7.47 million electron volt. So 14 is somewhere over here. When you draw a line like this, so this is where 14 is, and the corresponding value here is going to be 7.47 million electron volt. Is it clear?
Yes, sir.
Yes. So now you understood for each element what they are going to do. They are going to calculate the values like this and they will put it here. So the reason why I explained this concept is, see, I'll be sharing this work, this notes, okay, after this chapter is over. These points and all you can go through it. You can do a self-study. The reason why I explained this concept is for you to understand this point. If you take the lesser amount of binding energy for lighter and heavier nuclei, so lesser is the binding energy, more unstable they are. So the lesser amount of binding energy for the lighter and heavier nuclei. So lighter nuclei is this side. Okay, lighter nuclei is this side. Heavier nuclei will be this side. Okay. If you see the binding energy of them, they have lesser value, due to which they undergo the concept of nuclear fusion and fission respectively. So large amount of energy in the process of fission and fusion will get released. So see, a large amount of energy will be liberated if lighter nuclei are fused to form a heavier one, or if heavier nuclei are split into lighter ones. Okay, this is what happens, and that is the reason why this binding energy curve is very, very, very important. Is it clear? Okay. So after this, as I told you, radioactivity is not there. Then we need to discuss the concept of nuclear fission and fusion. Okay, we need to discuss the concept of nuclear fission and fusion. This part I will finish it tomorrow. With that, this chapter will be over. I have discussed a problem also. That is the only problem that is there. Had radioactivity been there, there would have been good problems. Okay. But since it is not there, we'll be discussing about the nuclear reactors and nuclear fission and fusion. Am I clear, guys? So it is a very simple chapter. I suggest everybody to go through it again. Okay. Yes, any other doubts from today's session?
No doubts, sir.
No, sir. No doubt, sir.
Okay, then we can wind up. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.